Hi students, good evening and welcome to this sessions of sum up series, and we are continuing with the network subjects. So today I have selected the topic network theorems, and this is one important topic. Okay, so although there are so many theorems like superposition, Thevenin, Norton, reciprocity, Milliman's theorems, compensation theorems, and so on and so forth. But I can tell you, most of the cases, 95% of the cases, the questions are generally targeted from the Thevenin and the maximum power transfer theorems. I hope you know, like Thevenin theorems and Norton theorems are correlated by source transformations. If you have Thevenin, you can get the Norton and vice versa. And if you are good in solving Thevenin questions, then indirectly you are also good in solving the questions which are based on the maximum power transfer theorems. Okay, so majorly your focus should be on the Thevenin and maximum power transfer theorems. So some basics, let me quickly revise, and then we'll be switching into the question segments. So any circuit which is containing RLC elements and sources, it is said to be linear circuits. And in linear circuit, any arbitrary voltage or currents, they can be represented using such equations, where this K1, K2, K3, K4 are some kind of constants. One important fact here that it is useful sometime. So superposition is not applicable for the power, right? So if you have a scenario like you have a circuits where you have multiple sources like this V1, V2, I3 like this, and if it is given that the power at Rx due to V2 is this much, I3 is this much, and V1 is this much, that means the individual power is given, and then they'll ask you if all the sources are acting together, what is the total power? Then in that case, you cannot do that PT is equals to P1 plus P2 plus P3. This is not equals to, okay? Note that PT is not equals to this. So if you have the individual powers, P1, P2, P3, what is the total power if somebody asks you? This is what is the corresponding formula. And how is it happening in the theory? You know, I have given the derivations. Otherwise, you just remember this. Okay. Then coming to the maximum power transfer theorems. So what information that you need is, so you know very well, any arbitrary circuit can be represented by its Thevenin model, right? So here intentionally, I have taken this is VTH and RTH. And this is some kind of load. So in this case, I have taken a resistive load intentionally, but this load is not necessarily to be resistive. It can be any other arbitrary kind of load. But one compulsory condition that what you need is, in this case, the load must be variable one. It should not be the constant one. So here the first point, it is applicable if and only if the load is variable. That is, if load is constant, then those circuits should be handled with other circuit analysis. That means if the load is constant, so that circuit doesn't come under the discussion of this maximum power transfer theorems. So when maximum power transfer happens is there are different ways to interpret it. But one of the fact that you should always remember is, so if this is a variable load and somebody is saying that maximum power transfer is happening to the load. So whenever somebody is saying like this source voltage VTH, it will be divided equally across RTH and this RL. That means under maximum power transfer condition, drop across RTH will be VTH by 2 and drop across RL will be VTH by 2. So naturally it makes sense if the voltage is VTH by 2 here and this voltage VTH by 2. So naturally the voltage are same, they are in series. So this resistance equal to this resistance. So sometime we say, like if it is a resistive case, RL equals to RTH for maximum power transfer. And what is the amount of maximum power transfer? Is VTH square by 4 RTH. So this much of information is enough for maximum power transfer theorems. Okay. And if you are good in Thevenin, you can easily answer the questions of maximum power transfer theorems. So here, combiningly, this is the discussions for Thevenin and Norton theorems. So you see here, this box, okay? So this is containing independent source, dependent source, and RLC elements. To this, externally, we have a load here. I mean, the ZL, okay? And the voltage is VL, and the corresponding current is IL. So what the Thevenin theorem says is, so from this AB terminal to the left of AB, so this complicated network, which is containing so many sources, so many elements, it can be represented by a practical voltage source, that is the Thevenin theorems, and it can be represented by a practical current source, that is the Norton theorems. In both of the cases, if you see, this is your AB, right? This is your AB. This is also same AB, okay? So to the left of AB, so in this case, we are replacing it by a practical voltage source, which is VTH, ZTH in series. In this case, we are replacing this one by a practical current source, which is IN and Z. And do remember the Thevenin equivalent and Norton equivalent. So one can be obtained from other one using the source transformation. That means if you know this is the Thevenin equivalence, using source transformation, we can get the Norton equivalent. Or if you know this is your Norton equivalence, using the source transformation, you can get the Thevenin equivalent. An important fact here is that this is what you should know. How to get the Thevenin. So Thevenin theorem, if you see, okay, so it is having two parameters, namely VTH, ZTH. Norton theorem, if you see, it is having two parameters, IN and ZN. So how do you get VTH? To get VTH, the corresponding load should be open circuits. So that's what I'm showing here. So you have to make the load open circuits, and you have to find the open circuit voltage. That is your VTH. Similarly, to get the Norton currents, you have to short circuit the corresponding load. So in this case, the load is short circuited, and the short circuit current we are saying is equals to Norton currents. Okay, and this information that all of you should know, that this voltage, I mean VTH and IN and ZTH, so they are related by this formula, because we said so one can be obtained from other one using source transformations. Here, if I'm saying that this is obtained from source transformation of this one, then if I ask you what is this IN, then this IN is VTH by ZTH. And what is this ZN? ZN equal to ZTH. So always remember, ZN, the Norton resistance, is equals to the Thevenin resistance. ZN equal to ZTH. But Thevenin voltage and Norton currents, so they can be related by this ZTH. Like IN is equals to VTH by ZTH, or VTH is equals to your IN into ZTH. But we have different circuits actually. So broadly, we have three kinds of circuits. So what are the circuits? So one circuit is what? One circuit is you have only independent sources with no dependent source. One case is you have only dependent source. Another case is you have both independent as well as dependent source. Okay, na? So let's start with some questions. So these questions, if you see, okay, I have taken it from related to maximum power transfer theorems. In the circuit shown below, maximum power transfer to RL is P max. Then what is the value of RL and what is the value of P max? That means we are given with a circuits where we have only independent sources. So we are supposed to find what is the value of RL, so that maximum power will transfer to this, and what is the amount of maximum power transferred. Okay. So how do you solve this problem? So the first thing in this case is, so because it's a resistive load, okay, for maximum power transfer to happen, the condition is RL equals to RTH. So you have to get RL, and RL equals to RTH. So how do you get the value of RTH in this case? To get the value of RTH, because it is containing only independent sources, the independent voltage sources should be sorted, independent current sources should be open circuits, and then you have to find the value of RTH. So if I ask you what is the circuit to get RTH, so I'll be referring the same circuits, but I'll be replacing that voltage source by short circuits. And then I have this 6 ohm and this load, okay, from here I want to find. So this is, I mean, this resistance is what I'll be telling RTH. I mean, I have to open circuit the load. From that terminal, I have to find what is RTH. So this is 6 ohms. Then I have 2 ohms. Then I have 4 ohms. And then I have this current source. And this current source is open circuited. Okay, na? So this 24 volt source is short circuited, and this 6 ampere source is open circuited. So from here, you have to find this value of RTH. So if I ask you, so what is the value of RTH? I mean, what is the equivalent resistance in from this particular terminal? That is 6 parallel with 2 plus 4. Because if you think you have a source here, so there are two paths. One is this path, another one is this path. So this path resistance is 6. This path resistance is 2 plus 4. So it is 6 parallel with 6. This is basically 3 ohms. So the answer could be either B or C, because in this case, RL equals to 3 ohm. So that means the value of RL for maximum power transfer is 3 ohms. And what is the maximum power transfer? We said it is VTH square divided by 4 RTH. VTH square divided by 4 RTH. If you remember, this is what I have shown you now, that the maximum power transfer is VTH square divided by 4 RTH. So that means we got RTH. Now we have to get VTH. Now, how do you get VTH? To get VTH, so what I have to do? The corresponding load I have to make open circuits. If I'm doing open circuiting the corresponding load, how does the circuit look like? So this is your 24 volts. This is your 6 ohms. Okay. So this load is open circuits. So this is your 2 ohms. And let me do one thing. For simplicity, so let me apply source transformation to these segments. If I apply source transformation to these segments, so this is your 4 ohms and 6 into 4, 24. So you'll get here 24. Okay. So this is what is the cases. So which voltage VTH? So your this voltage VTH. So if I ask you, so how do you get the VTH here? There are multiple ways, but one thing I can tell, in this path the current is I equals to 0. Why? Because this is 24, this is 24. So the current in this, it's a series path, is 24 minus 24 divided by 6 plus 2 plus 4. So this is basically 0. So if the current is 0, there is no drop. Okay, if there is no drop, so this voltage is 0. So if I ask you what is VTH, so your VTH is equals to 24 in this case. So P max, the maximum power transferred, is VTH square, which is 24 square, divided by 4 into 3. That is 24 into 24 divided by 12. So this is basically coming 48. So the answer is C. So RL is 3 and the amount of maximum power transfer is 48. Okay, na? This is what the analysis is. Hopefully all of you are getting the same answer. But suppose if somebody is asking you to tell what is the Norton current in this case by taking the same RL as the load, then you can calculate IN independently. Otherwise, you can make use of the formula IN is equals to VTH by RTH. So what is your VTH? So VTH is 24. And what is your RTH? RTH is 3. So 24 by 3, that is 8 ampere. So the Norton current is 8 ampere. In case if it is necessary, the answer is 8 amperes. So in this particular problem, I have touched the Thevenin theorems, Norton theorems, and maximum power transfer theorem. But the model of this circuit in this case is it is containing only the independent sources. So the next question I have taken. So in this case, we have independent sources and we have dependent sources. So here the question is, what is the voltage V in the following network? Okay. So to get the value of V, we can have other technique, but here my interest is, I'll be interested to calculate the value of V using the Thevenin theorems. Okay. So of course in the GATE exam, nobody will tell you evaluate these, that using this method, that methods. But here my interest is to solve this using Thevenin theorems. Or we want to practice a questions where the circuit is containing both independent as well as dependent sources. See, in GATE exam, one question compulsory from theorems you are getting every year. So the question can be from DC or AC, but the concept remains same only, right? So there you deal with only phases. Here it is the normal mathematics. Okay. So tell me. So how do you get this one? So the technique in this case is, so let us say This is your node A. This is your node B. So the network, okay, from AB terminal can be replaced by the Thevenin model, which is VTH, and you have RTH, VTH, RTH, and this is what you're the same AB terminal. That means from AB terminal, the rest part of the network can be replaced by a Thevenin model. So this is your 1 ohms and this is your V. And if I ask you what is V, so V by voltage division rule is 1 divided by 1 plus RTH multiplied by VTH. Isn't it? So in this case, so I have to evaluate what is the VTH and what is RTH. If I do it, so my problem is over. So first, let us work on evaluating VTH. So how do you evaluate VTH? To evaluate VTH, you have to open circuit the load. Which is the load? So this 1 ohm is the load. So let me redraw the circuits. This is 2IX. This is 1 ohm. This is also 1 ohm. This is 4 ampere. This is 1 ohm. And this is your IX. This is your 1 ohm. This is minus, plus. This is 24 volts. And this is now open circuits. Okay. And this particular voltage, so we'll be calling this is VTH. We'll be calling this as VTH. Anybody, what is the answer? Anyone, what is the answer? Anybody solved it? So here if you see, okay, so this direction current is 4 ampere, right? This is 4 ampere. So at this node, because this path is open, the same 4 ampere will flow this way. Yes or no? So if I ask you what is the voltage across this 1 ohm resistor, so this is plus, minus, current is 4, resistance is 1. So this is basically 4 only, 4 volts. Now, if I write this one, I mean the KVL equation at this mesh, I'll be getting what is VTH. So if I write that, I'll be getting VTH minus 4 plus 24 is equals to 0. So VTH is equals to 4 minus 24. So what is VTH? VTH is minus of 20 volts. So the Thevenin voltage is minus of 20. So V is equals to minus of 20 divided by 1 plus, we have to get the value of RTH now. So hopefully all of you are getting the same answer. So very simple. You see this circuit is looking so complicated. But once I'm open circuiting this, the same 4 ampere current is passing in this path. So if I'm writing a simple KVL equation at this particular path, so I'm getting this one, VTH minus 4 plus 24 equals to 0. VTH is equals to 4 minus 24. VTH is minus 20. So now do let me know how do you calculate RTH. Now to evaluate RTH in such kind of cases, I mean the network which is containing both dependent as well as independent sources. Generally, there are two approaches. One of the approaches, evaluate this IN, then you can get the value of RTH using the formula VTH by IN, right? We have already the VTH. If you get IN, we can use this formula to get it. Otherwise, if you don't want to do that, one more technique, what you can do is you can deactivate all the independent sources. Like you can make this is open circuit, this is short circuits. Then you connect a test source here and find the voltage to current ratio. That will give you the RTH values. In this case, I'd like to go with this one. I'll be taking one more questions where we'll be going by that approach. We'll be connecting, say, test source and we'll be finding the V2I ratio. But in this case, I want to have the IR informations, and from there, I'll be evaluating RTH. So to evaluate RTH, okay, so first I'm getting IN. So how do you get IN? Now to get this IN, so again, I'm drawing the circuits. So this is your 2IX. This is 1 ohm. This is 4 ampere. This is 1 ohm. This is IX. This is 1 ohm. This is 1 ohm. This is 24 volts. And this is short circuited. So this current is your Norton current IN. In the previous case, the corresponding load terminal is open circuited. In this case, I am doing it is short circuits. Okay. So if you do it short circuits, so how do you get the value of IN? Anybody? What is the answer? Can you respond? What is the answer for this IN? What is the IN then in this case? Think this way. This thinking skill will only help you in the exams. So the circuit, what you'll be getting in the exam, it will be new circuits. You have to think where I'll be writing the equations and also that I'll be getting it. And with respect to experience, I mean, it won't be very challenging. So in this case, what I can tell is, do you agree that this voltage will be same minus and plus? This is 24 volts. I mean, in other words, do you agree that this 24 volts and this 1 ohm resistors are in parallel? Yes. When two elements are said to be in parallel, if they're between same pair of node. So if I'm saying this is node A, if I'm saying this is B, the entire path is B, na? So this is connected between AB and this source is also connected to AB. That means they are in parallel. So the voltage across the 1 ohm resistor is 24 volts with the same polarity. I mean, this side is minus and this side is plus. So if it is 24, so like if I ask you what is the current, so this direction current, because in a resistor, the current enters through plus to minus. So because the voltage polarity I have given, so the current is from plus to minus. So what is the current? This current is 24 ampere because voltage is 24, resistance is 1. 24 by 1 becomes 24 amperes. So at this particular node, now you can write a KCL. So what is the incoming current? Incoming current is 4. What is the outgoing current? 24 plus IN. So what is your IN? Your IN is 4 minus 24. So that is minus of 20 amperes. So VTH is minus 20 and your IN is also minus 20 amperes. Now, if IN is minus 20, so your RTH, as you said, it is the ratio of VTH to IN. So in this case, minus 20 by minus 20. So the answer is coming 1 ohm. So you got VTH is 20, minus 20, IN minus 20, and RTH value, you got it 1. So if I'm substituting this all in formula, so VTH, it is minus 20, 1 plus this is 1. So how much you get? It is minus 20 divided by 2. So which is basically minus of 10 volts. So what is the value of voltage V? The voltage V answer is minus of 10 volts. So this question, which was looking so complicated, by this approach, you see how simple it is now. Isn't it? So again, I'm telling, so this network was containing both independent as well as dependent source. But here, intentionally, I'm getting this VTH and IN, and then I'm taking the ratio to get RTH. The other method is deactivate all the dependent sources, and then you get the test voltage to current ratio. So that is what is the other approach. Well, let's take up this question. So the question here is, for the following network, VI curve with respect to terminal AB is given by. So you have to have the VI, the V and I are given for this particular load. Which of the following graph is the correct graph for this VI? Okay. So how do you deal with this? So the concept behind this is something like this. So as you know, if I have a circuit and to this externally I am connecting a load and the corresponding load voltage is V and the corresponding is I. Okay. So we know this box, this particular box can be replaced by its Thevenin equivalents. So this is your VTH and then you have your RTH. So VTH and RTH, and then you have this load. So this load voltage is V and this corresponding load current is I. So in this case, you can have these equations that V is equals to VTH minus IRTH. Yes or no? V is equals to VTH minus IRTH. So if you rewrite these equations, you can see here IRTH is equals to VTH minus V. VTH minus V. So what is this I? I is equals to minus of V by RTH, okay, plus VTH by RTH. So this is what is the equations. So once we get the value of VTH and RTH, and if you put in these equations, then we can draw this particular graph. So indirectly, again, the question is to evaluate the value of VTH and RTH. So the same informations, but it is twisted in a bit different way. So in this case, how do you get it then in this case? So let me first try to get the value of RTH. Now, if you try to get the value of RTH, it's the network which is having only independent sources. So what I'll be doing then? Then all the independent sources I'll be deactivating. So if I ask you to draw these circuits, so this is your 2 ohm resistor. So this is your again 2 ohm resistor. Then this is the current source which you open circuit. And this is the load from where you want to find RTH. And this is your 4 ohm resistor. And the 24 volt source is sorted. Okay. So this is 2, and this is your 4. So from this particular terminal, I want to evaluate what is your RTH. So what is your RTH now in this case? Anybody, what is the answer? What is the RTH? So if you observe carefully, if you think, so if I'm asking you to find the value of equivalent resistance from this particular terminal, how do you get? I think there is no doubt on this, right? So the current source 2 ampere is open circuited here, and the 24 volt where it was connected, so that segment is short circuited. Now, if I ask you what is the value of RTH, then what do you get in this case? So if you think like I am connecting a source here, so where the current will go? So the current will go to this path, and from this path, there are 2 paths. One is this path and one is this path. But the point is, so that means you can say, so if I ask you what the value of RTH, so value of RTH is equals to 4 plus, where this 4 is coming? So this is your 4 plus. From this point, there are 2 paths. What are the resistance of the path? One resistance is 0. I mean, this is sorted one, right? 0 parallel with, and the other path is 2 plus 2. So which is 4 plus 0 parallel with 4, which is 4 plus 0, which is 4 ohms. That means in this particular case, the value of RTH is nothing but your 4 ohms. Right? So value of RTH we got, it is 4 ohms. Now, but my formula needs, I mean this equation needs the value of RTH as well as VTH. Now to get the value of VTH, so you can make this one open circuits, you can find VTH. Otherwise, the other approach what somebody can try is, you can get the Norton current IN. And once you get Norton current IN, then VTH in that case is obtained using the formula IN into RTH. Because we said that IN is always the ratio of VTH to RTH. So VTH is basically product of IN and RTH. So RTH you already got. Now if I get IN, my job is over. So how do you get the value of IN? To get the value of IN, so the corresponding load should be short circuited. So if I ask you to draw the corresponding circuits, so how does the circuit look like? Let's have a look. So this will be something like this. So this is your 2 ohms. This is your 2 amperes. And this is short circuited. Okay, na? Because I want to find the IN here. So this current, I'll be telling it is IN. This is your 4 ohms. This is your 24. And this is your 2. Okay. So this current IN I want to find. So you take this point is ground. So if you take this point is ground, now if you see in this case, so this node voltage is 24, this node voltage is 0 volts. So what is the voltage here? So this voltage is 24. Because positive side, even this is 24, this is 0, so this is 24. So if it's 24, so if I ask you what is the current, so the current is 24 by 4, this is 6 amperes. So if you write the KCL at this particular node, the incoming current is 6 and the outgoing current is 2 plus IN. So what is IN? So your IN is 6 minus 2, which is 4 amperes. So RTH is 4. Now you are getting your IN. IN answer is also 4 amperes. Then what is VTH? So VTH is product of IN and RTH, which is 16 volts. Now, if I substitute all these parameters in this equation I mean in this one, so minus V by RTH. So it is minus 1 by 4 into V plus VTH by RTH. VTH by RTH is IN only, that is your 4. So you have to check now which particular equation is satisfying this one. Or if I want to plot it independently, so let me take I on the x-axis and V on the y-axis. Because that's the way all the options are given. I think it would have been easy to express the, okay, I didn't notice that. So otherwise I could have represented this V in terms of I. I mean, V equals to something in terms of I. Anyway, we can do this way also, no problem. Now, if I make here I equals to 0, if I make I equals to 0, so what is the value of V you get? If you make I equal to 0, so V is equals to how much? Minus 4, minus cancel, 16, na? 16. So I is equals to 0 and V is equals to 16. So a point you'll be getting here, right? So this coordinate is 0, 16. Next, you make V equal to 0. If you make V equal to 0, then you're getting I equals to 4. So if you're making V equal to 0, then I equals to 4. I mean 4, 0. X is 4, Y is 0. Some mistake is happening, right? 0, 16 is one coordinate and the other coordinate is 4, 0. 4, 0. So 4, 0 will come, X is 4 and Y is. Sorry, this point is not here actually. 1 second. So, okay, if I'm saying this is my point 1 and this is my point 2, where this point 1 is, X is 0 and Y is 16. So this is what your point 1 is and this is what your point 2 is. So if you draw it, okay, so point 1 coordinate is 0, 16. So you'll be getting here 16 and point 2 is, this is your 4. So if you'll be drawing this, This is how it will be looking like. And this line slope is minus of 1/4. Okay, and if you check it, this is matching with option A. So is the right answer. So the same questions they're asking in some indirect way. Hopefully this is clear. Anushka, Prakash, Tallam, okay, good. Your answer is A, right? Fine, good. Now let us answer these questions. Okay, so this is also a different model question I have taken. Here the question is, for the circuit shown in the figure below, the value of RTH is dash ohm. Okay, because if there is a single question from Thevenin, so from which particular model the questions will be, we don't know. So it is wise to touch up all the models. So I have touched up the questions which is containing only independent sources, and we have also seen the questions which is containing dependent independent sources. But these questions I have taken here, which is containing only dependent sources. In this kind of cases, what happens? Now, do remember, whenever you get the questions which is not containing any kind of independent sources, blindly you can say in this kind of circuit, always VTH is 0 volts and Norton current is 0 ampere. So always in any circuit, if there is no independent sources, if it is containing only dependent sources and resistor combinations, then VTH is always 0 and IN is always 0. So if VTH and IN both are 0, 0, then you can get the value of RTH. We have to get the value of RTH. RTH will be non-zero depending on the circuits. So now we need to check how to get the value of RTH. So how do you do is, so the normal method in this case is, so across the terminal where they're asking to find this RTH, so you have to connect a test source. So I'm connecting a test voltage source VT, and the corresponding current, let me name this is your IT. And then this RTH is nothing but the ratio of VT to IT. Okay, so you can connect a current source. Ultimately, we need the voltage to current ratio from the terminal. Okay, so tell me, how do you solve this question? By observing this one, I mean, here the IX is present, right? This is your IX, and this is my IT. So this is IX is going this way. So what I can tell by observing the circuits, I can tell one thing, that in this particular circuit, your IX equals to IT, because it is the same path, no? This is the same path. IX is equals to IT. And then apart from it, if I observe this particular node, so from this segment, minus 2 IX is coming, and from this segment, this IT is coming, right? So if I ask you what is the current which is passing through this 100 ohm resistor, so this is the sum of these two branch current. I mean, this current and this currents. So what is the current? Then this current is your IT minus 2IX. And 2IX, in place of IX, I'm writing IT. So IT minus 2IT. IT minus 2IT is minus of IT. Anyway, let's write IT minus 2IX for the time being. So this branch current is, so the sum of this and the IT minus 2IX. Okay. And IX is VT, we said. And what is VX? So VX is, this voltage is VX. This is what is VX. Now, don't you think VX equals to VT? Yes, because across that only you have connected the test voltage source VT. So VX equal to VT. Now, if I ask you what is the current in this branch? So in this branch current, I mean, if you see this particular node, there are 3 branches are there. So the current in this branch is IT minus 2IX. This is 0.01 VX. So if I ask you what is this current, so this current will be IT minus 2IX minus 0.01 VX. Hopefully you agree. I mean, this much of current is approaching this node and this much of current is going away. So this particular current minus this particular current is the current in this branch. So this current is IT minus 2IX, this one, minus of 0.01 Vx. That is the current in this particular branch. Now it is very simple. I'll be writing a simple KVL equations. If I do that, so anyway, so what is this quantity, by the way? Let us write in terms of IT VT. So this is your IT minus 2IT minus 0.01 VT, which is basically minus of IT minus of 0.01 VT. This is this current. So if I write the KVL equation now, Vt minus of 100 into the corresponding current, It minus 2Ix. It minus 2It, which is minus of It. So Vt minus 100 into this particular current, which is It minus 2It is minus It. Okay. Then minus of 300 into the corresponding current, which is minus It minus 0.01 Vt equals to 0. Okay, na? Vt minus 100 into minus It minus of 300 into the corresponding current, which is minus It minus 0.01 Vt equals to 0. Now, if you simplify this equation, now you can see this entire equation is only in terms of Vt It. We can rearrange them and we can take the Vt It ratio. If I do that, what do you get? So Vt plus 100 It, okay, plus 300 It, again plus. So this is 3 Vt equals to 0. Hopefully, I am not doing any calculation mistake. Vt plus 100 It plus 300 It plus 300 into 0, this is 3 plus 3 Vt equals to 0. Now, if I club the terms, 4 Vt, 3, okay, 4 Vt plus 400 It equals to 0. Okay. Right. Then the Vt to It ratio, 4 Vt is equals to minus of 400 It. So Vt by It is equals to minus of 100 ohms. So this is what your RTH is. Check the calculations, but you shouldn't be surprised if the RTH answer is coming negative sometimes. Okay, RTH can be positive, RTH can be negative. But what it matters is you are not doing any calculation mistake. But you shouldn't be surprised by observing this negative sign. RTH is not necessarily to be always positive. The logic is clear. Please check, is there any calculation mistake if I have done? Otherwise, this is what is the approach. So this is a homework for you people. Okay. The question is the VI equation for the networks shown in the figure is given by what? So the approach in this case, let me give you, but this is your responsibility to solve it. So this network is again containing, we have this what? Dependent source as well as independent source. Okay. Because it is containing dependent and independent source. Okay. You have your own ways to get the VTH and RTH, the techniques what we have seen today. Then what I can tell is the network which is connected to the left of this AB terminal can be replaced by a Thevenin model, which is VTH, and the resistance, which is RTH. Okay. This is what the circuit is. So this is what your V and this is what your I is. So if you observe this, what I can tell is V is equals to VTH plus RTH into I. If you write the KVL, V is equals to RTH into I plus VTH. So you get the value of VTH and RTH and you substitute in these equations. So that if you see all the options, so V is expressed something like this. Something multiplied with I with a constant. So this constant terms are indicating VTH and which is multiplied with I. So they are indicating the value of RTH. Okay, you please try this. And if you try this, the answer that somebody is supposed to get is, let me tell you what is the answer you're going to get. So this answer is option C, which is 254. That means the value of VTH is 54 and the value of RTH is 200. Please try it out, substitute in these equations, and you see whether you're getting this option C or not. Okay, so this is what is the kind of questions you can expect in the GATE exam from the network theorems. If there is a single question is from network theorems, most likely it is from this particular Thevenin theorems or maximum power transfer theorems. So having said that, so let's go into the next topic, okay? So which is basically the inductors and capacitors. Okay. So inductors and capacitors. So in this case, what is important for you people to know it? Let me quickly brief it, and then we'll be going into the question sections. So in this inductor and capacitor, so the voltage and current equations are essential. Okay. So you know very well, VL is IC is equals to CD by dt. VL is equals to LDL by dt. And VC, I mean the capacitor voltage is given by these equations. Inductor current is given by these equations. But while writing such equations, the polarity and the current direction should be fixed in your mind. The current always enters from plus to minus, both in case of capacitors and in case of inductor. The current is always from plus to minus. So that you shouldn't forget. And apart from it, a practical circuits of capacitor is R in parallel with C. In case of inductor, R in series with L. Okay. So, and rest of the things, the common things only. But still, let me touch it. So, you can go through these notes, okay, in handbook. I mean, in case if you are not good in the theory. Otherwise, if you have done with theory, then let me come into the point directly. I mean, this is what is the corresponding current division rule and voltage division rule with respect to inductor capacitors. Here, one important fact is, whenever a bunch of capacitor are in series, then the individual charge must be same as equivalent charge. Okay, that means if you have this, capacitors C1, C2, C3. Okay, so it is compulsory that their charge will be same. I mean, you cannot have Q1, Q2, and Q3. Whenever capacitors are connected in series, their individual charge must be same. But in parallel, there is no such constraint, like it can be Q1, Q2, and Q3. And whenever capacitors are in parallel, and if you know their individual charge contain, then the total charge stored is sum of the individual charge. So if the individual charge are Q1, Q2, Q3, then the total charge is Q1 plus Q2 plus Q3. But in this case, if all capacitors are carrying Q1, 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 the total charge stored in this equivalent capacitance is still Q1. Don't say that it is Q1 plus Q1 plus Q1. So this is important. So based on this, some question I have taken. Let me see. Let us solve this particular question here. So here the question is to evaluate what is your LAB. So what is the equivalent inductance? Like we have seen questions which are, like you have to solve, you have to get what is R equivalent. So here I want to get what is the L equivalent. Anybody, what is the answer in this case? What is the value of this L equivalent in this case? Anyone, what is the answer? For your understanding purpose, so this node is A. So this is A, and this node is also A, because no element in between, this is A. Let's say this is your C node. This is your C node. This is B, means this is also your B. So I'm redrawing the circuits. Okay. So there are three nodes basically. So let's take this is node A. Let's take this is node B. So if I ask you where this 20 million is connected between A and B. So between this A and B, so 20 million I'm connecting. This is 20 millihenry. Okay, so this inductance I have connected. Then if I ask you where this okay, so let's take a third node, which is C. Okay, so let's take a third node, which is C. So if I ask you where this 30 million is connected between A and C. So between A and C, we have 30. So this is your C. So between A and C, you have 30. Then if I ask you where this 60 is connected, it is again between A and C. So again between A and C, you have 60. So this is your 60. And where this 10 is connected, so this 10 is connected between B and C. So this is your B and this is your C. So this is how much? 10 millihenry. So how many inductors are there? 5 inductors are there. So 4 I have drawn. And where this 60 is connected, this 60 is between A and A. So that means it is sorted only. So you don't get anything from this. It is sorted. Right. So what is your LAB? So the simple logic is if both points are sorted, okay, I mean the net inductance is 0 only, like the case of resistors. What is LAB in this case? It is 20 parallel with 30 parallel with 60 plus 10. So it is 20 parallel with 30 parallel with 60 is 20 plus 10, which is 20 parallel with 30, which is 600 divided by 50, which is basically 12 millihenry. Okay, so the LAB answer in this case is 12 millihenry. Let us try to answer this beautiful question, okay, which is based on this charge concept of this capacitors. Okay, so see the questions and please respond. The question is, in the following network, charge in capacitors C1, C2, and C3 respectively. So we are supposed to get the charge of C1, C2, and C3. Okay, how do you get? We said one concept. In series, the capacitor contains same amount of charge, and the charge in the equivalent capacitance is charge of individual capacitance. But once you are connecting the capacitor in parallel, the total charge is sum of the individual charge. Okay, now. So the way to solve this one is, let me redraw the circuits. If I redraw the circuits, so do you mind if I am shifting this point to this point? I mean, like this, if I'm erasing this one, because the same point, na. So in that case, if I ask you, okay, so this circuit is equivalent to something like this. This is your 10. So this is so this is your 8 microfarad, this is your 10, and this is your 12 microfarad. So in this case, I can replace it by a single capacitor, right? So what is this net equivalent capacitance from this particular source? 10 and 8 are in parallel. So this equivalent capacitance is 10 plus 8 is 18. And 20 and 0. So these are in parallel, right? Sorry, 12 and 0 these are in parallel. So this is your 12. Hopefully you agree, right? In capacitance, when they're in parallel, we used to add their values. So 12 parallel with 0 is 12. And 10 parallel with 8 is 18. So equivalently, I have two capacitors which are connected in series. So I can tell the original circuit is equivalent to 10 volts, is in series with a capacitor which is 12 microfarad. And this is in series with a capacitor whose value is 18 microfarad. This is 12 and this is 18. So what is the equivalent capacitance if I ask you? So the equivalent capacitance is, C equivalent is 12 into 18 divided by 12 plus 18. So if you simplify this, so this answer is coming 7.2 microfarad. So this answer is coming 7.2 microfarad. So that means, so this circuit, okay, is something like this. So this is your 10 volts and you have a single capacitance, so which is 7.2 microfarad. We know the relations. Q is equals to C into V, or Q equivalent is equals to C equivalent into V equivalent. So C equivalent is 7.2 microfarad and V equivalent is 10 volts. So the Q equivalent is 7.2 into 10, which is 72 microcoulomb. Which is 72 microcoulomb. That means this particular equivalent capacitance is storing the charge 72 microcoulomb. And one thing I can tell, so this 7.2 microfarad is result of series combination of 12 and 18 only. Yes or no? This is the result of series combination of 12 and 18. That means if this equivalent capacitance is storing 72 microcoulomb of charge, it means this 12 and this 18, they're also storing the same 72 microcoulomb of charge. So if I ask you, what is the charge contained in this 12 microfarad capacitor? So this is your 72 microcoulomb and this is also your 72 microcoulomb. This is also 72 microcoulomb. Now, this particular 18, okay, so this is the result of parallel combination of this 10 and 8. Yes or no? And so that means what I can tell is, as of now, I already obtained the charge of this 12 microfarad. So this is 72 microcoulomb. And if you see the options, option C will satisfy this. But let us see how this 40 and 32 are coming. So 72 is confirmed, okay? I mean, for 12 microfarad, the charge storage is 72 microcoulomb. Now, what about the charge of this C2 and C3? So one thing I can tell, that this particular, 18, this 18 is result of parallel combination of 10 and 8. So that means if this is storing 72 microcoulomb, what you can tell is this parallel combination is storing 72 microcoulomb. So that's why if you add this 40 and 32, so the sum of this is coming 72. Because we said in parallel, if we add the individual charge, we'll get the total charge. So the charge content of 10 and 8, sum of them will be 72 microcoulomb. Okay. Now, so how do you get the individual charge then in this case? So you know their individual capacitance. So how do you get their individual these things? So the wise thing is, you first get what is the voltage. What is the voltage? You try to get it. So that means if you have two capacitors are in series like 12 and 18. Now, if I ask you, what is the voltage of this 18, this one? So how do you get it? You'll be writing the voltage division rule. So voltage across 18 microfarad capacitor is 12 divided by 12 plus 18 into 10. Hopefully, you know. I mean, if you have two capacitor, so if you want to get the voltage across C2, so you have to write C1 by C1 plus C2. So the logic of this, I think, probably know that. So this is coming 120 divided by 30, so which is coming 4 volts. So this is coming 4 volts. So that means, so this voltage is basically 4 volts. So now, so the voltage is known is 4 volts, and you know their capacitance. So capacitance value in one case is given 10. So what is the charge? Because Q is equals to CV. So C into V, 4 into 10, that is 40 microcoulomb, one case. I mean, for this 10 microfarad capacitor, so the charge storage is basically 40 microcoulomb. How do you got it? I got their voltage first. So voltage I got is 4. Once I get voltage, I know the capacitance 10. So Q is equals to C into V. And next for the C3, it is again Q is equals to C into V. So C value is 8 and voltage is again it is 4 only. So 8 into 4. This is your 32 microcoulomb. So hence the answer is 72, 40 and 32. This is the answer. Okay. So like this, we have some other question as well. So tomorrow we'll be taking up them. So that's what all for today. Students who are watching it live, please give a thumbs up. And tomorrow again we'll continue, from this, and we'll also have the